Okay, great. Good afternoon, everyone. Thank you for staying until the end of our student talks. I'm happy to talk to you guys today about research related to my project in quantum metrology. So what is metrology? Metrology is the science of measurement, and measurement standards have been an important part of all of human history. Even in ancient times, it was important for people to agree on definitions of units of measurements for building buildings, weighing masses for commerce, and even in ancient Egypt, their unit of measurement was the length of a forearm and was called a cubit. Ironically, has nothing to do with quantum bits. But as time progressed, they needed more and more precision in measurement. So in the 1800s, the metric system, which was the basis of the SI units, were created. But these physical artifacts to define a unit of measurement have two major problems. First of all, for example, if we look at this meter stick, everyone who's talking about meters would need to calibrate their meter to this 1 meter stick. That's the definition of what a meter is. And as well, these physical objects can change over time, and that is a huge problem. We don't want our definition of units to be changing over time. So science has been moving towards defining units of measurement based on fundamental constants of the universe, which are values that are universal and don't change over time. For example, the speed of light, charge of the electron, Planck's constant, or in atomic clocks, the hyperfine transition in cesium atoms. So let's see how they were able to define units using these physical constants. So we took our existing definition of a unit, so a meter, which used to be defined by a physical object of the size of 1 meter, and use it to measure the physical constant with those units at the highest precision that we can. Then define that physical constant to be exactly this number in those units. So we can say that this is exactly the value of the speed of light, because the speed of light exists regardless of what units are chosen. And here in this case, then the units are chosen such that the speed of light will be exactly this number in meters per second. So then we can redefine the length of a meter based on the distance that light travels in exactly this amount of time. And this process has been used to define all of the SI base units on which all units of measurements are based. And in this project, I'm focusing on the voltage standard. As we can see, is not one of the fundamental units, but the voltage standard is actually used to link the kilogram to Planck's constant, which is kind of hard to imagine the link between kilogram and Planck's constant. So the Josephson voltage standard is used to define the voltage based on only fundamental constants of the universe, using a Josephson junction, which is made of superconductors separated by an insulating barrier, which is also the building block for superconducting qubits. Normally, we expect the voltage of an object to depend on its physical properties, the material, the size, basically its resistance. But in this case, when we apply microwave radiation to a Josephson junction, we observe a DC voltage that depends only on Planck's constant, charge of an electron, and the frequency of that radiation. And as mentioned previously, frequency is traceable to the cesium atomic clocks standard. So this value of voltage depends only on fundamental constants of the universe. So to look a bit at how this works, we need to first look at superconductivity. And as was kind of hinted earlier, superconductivity, when people think of it, they might think of just a perfect electrical conductor, zero electrical resistance. But it's not just that. It's a unique quantum state of matter that also experiences the other effect like perfect magnetic field expulsion. So looking at how superconductors arise, let's first look at normal conductors, at their resistance versus temperature. So heat causes vibrations of atoms, and resistance corresponds to barriers that make it difficult for electrons to propagate in a material where they do collisions with atoms. So with hot atoms, electrons are more likely to have a collision with these vibrating atoms, which leads to a higher resistance. So as we cool down, we expect the resistance to lower as electrons have more ease of traveling through the material. But even at the lowest temperature, we still see a finite resistance in conventional conductors, since the impurities in the material still cause some collisions to slow the electrons down. With a superconductor, we start with a similar behavior, but when we reach a critical temperature, suddenly the resistance drops to exactly 0. For a niobium, which is a typical superconductor, that happens at 9 Kelvin. Let's see a bit what's going on here. So at that temperature, suddenly we have a phase transition to a new state of matter where the electrons form what we call Cooper pairs. And as earlier, as our colleague explained, fermions and bosons, electrons are fermions, but now these Cooper pairs behave as bosons. So now suddenly all the electrons can form together one quantum state. So the whole superconductor can be described by this one wave function with an amplitude and a phase. Though even if there are impurities, it doesn't affect the conduction of this whole quantum state. So now looking at our Josephson junction, this consists of two superconductors separated by an insulating barrier. So if we measure that insulating barrier or that resistor, we would see a finite resistance. But when we add a superconductor on each side, normally you'd think adding wouldn't decrease the resistance. But suddenly with superconductor on each side, the resistance measured is exactly 0. And that is because of quantum tunneling. So the wave function of each superconductor, the macroscopic wave function describing the entire superconductor, have some overlap in the barrier. And this was actually the Nobel Prize in Physics last year for quantum tunneling on a large scale. And this is really important because it shows that quantum mechanics, which we think to be about really small particles, we only think quantum equals small. Quantum also exists for large systems. This was demonstrated in centimeter scale superconductors. So looking at if we apply a current and measure the voltage, knowing the relationship between voltage and resistance, in that regime that I just mentioned, where there's no resistance, we see no voltage. No voltage equals no resistance. But this is only true up to a certain current, after which the junction goes back to behaving resistively. And this is described by these two equations, which relate the current and voltage to the phase difference between the two superconductors here. So these equations are coupled. And without looking too deeply at them, if we rearrange the terms to have potential energy versus that phase, we can get a more intuitive picture of how the Josephson junction works. And that is with a potential called the tilted washboard potential. So here we see a ball in this sort of potential well structure. And the position of the ball corresponds to the value of that phase difference. And when we apply a current, we're changing the tilt of that potential. And since the voltage is proportional to the rate of change of that phase, if we see the velocity of the ball, so the ball rolling on this potential, this corresponds to observing a voltage. So we can see, as expected, even for regular conductors, if we don't apply any current, we don't see any voltage. The ball is trapped in this potential. But if we increase the current slightly, which is in that first regime of 0 resistance, we see that the ball is still trapped. So even though we have a current, we have no voltage. The ball is not moving, and this corresponds to that no resistance case of the Josephson junction. But if we increase further, past a certain point, then the ball will be able to roll down the potential, and the potential will not be able to trap it anymore, and then we see a voltage. So now let's see how the Josephson junction can be used for a standard by applying microwaves. So these can be applied from antennas, waveguide, coaxial cable, etc., and correspond to microwave frequency electromagnetic radiation, which gets coupled as an additive AC current term to our current drive that set the tilt, as mentioned earlier. And when we do this, we observe these steps where we see these constant voltage steps that are separated by our HF over 2E, so our quantized voltage steps. So all of these steps only depend on fundamental constants of the universe and not on any physical properties of the junction that we are using. And to just give you kind of a ballpark value, this conversion constant is 484 megahertz per microvolt. So a single junction, if we radiate gigahertz microwave frequency, will only produce microvolts. So to get a 1 volt standard, we add up many of these junctions in series. So all the voltages add up to 1 volt. So now looking back to our tilted washboard, let's see how this works to observe these Shapiro steps behavior. So as I mentioned, our microwaves add an AC drive, which then will cause a time varying tilt of that potential. And when that tilt frequency matches the period of motion of the ball in the well, it's able to retrap it, leading to a constant voltage despite a higher, a constant voltage despite a higher current. And the higher order steps come from locking to higher order periods. So the motion of the ball through 2 wells or 3 wells within that period of the AC drive. So this leads to these different ranges of voltage steps. So now looking at state-of-the-art devices. Here, this is a programmable Josephson voltage standard, which is used in NIST in the US. And we can see this, the size of the chip here is in the centimeter range, but the size of the entire device operating it is really big, as we need to cool this below the critical temperature of niobium, which I showed earlier was 9 Kelvin. And this is made up of 270,000 junctions in series. And with it, we're able to produce a variety of voltages. So it essentially acts as a digital to analog converter, where there's voltage taps at different numbers of junctions to have different bits of resolution. And you can create multiple waveforms or different quantity of voltages that are all traceable to fundamental constants of the universe. And here at the University of Waterloo in Corey Lab, we're working on the next generation of voltage standards, making them more accessible to Canadians and beyond. So Canada currently relies on the US's JVS, and we can all see how that is problematic. So we're working towards creating the standard for Canada, as well as innovating by using higher temperature superconductors. And this will mean that we don't need all these big, complicated, fancy cooling equipment. We can use smaller cryogenic systems, and thus making the standard more accessible and affordable. So imagine a world where each research lab could have their own quantum voltage standard. And it is exactly the realization of a volt. They never need to see any other voltage standard. They never need to calibrate with anything. They already know they have the true definition of a volt in their lab. And what this looks like. So here is one of our prototype devices of some junctions connected to this microwave transmission line and these DC lines to make these electrical measurements to try and observe these Shapiro steps. And the way that we make the junctions is by growing on an entire wafer a layer of superconductor, insulator, and superconductor in these ultra-high vacuum growth chambers here on campus in Rack 2, where we essentially evaporate these materials and then controllably deposit them back to form these layers. Then in the nanofabrication center here in QNC, we selectively etch to define the junctions and connect them in series. So if you're interested in being part of this, this is a great time. As technologies are getting to smaller and smaller signals, we need more and more precisions. And as we're on the edge of the quantum frontier, having quantum measurements and quantum sources is even more important. So thank you very much for listening to my talk, and thank you to these supporters.
Thank you so much for that wonderful talk. We have time for Q&A. Feel free to raise your hand.
Thank you so much for the talk. I was wondering, the last slide just now, is there a particular reason for the different choice of material in that setup, and the thickness and the shapes, etc.?
Okay, yeah. So as I mentioned, the value of the voltage does not depend on any of the physical parameters of the device. But to be able to see those voltages, you do need to be working within a certain range of materials, thicknesses, and so on. So it is not easy to observe these Shapiro steps for the first time. But once you have your system working, then forever they'll be able to produce that quantized voltage. So so these particular materials were chosen for these higher temperatures. But going from left to right, these are kind of an ease of fabricating Josephson junctions from them. So even though this niobium nitride is only a few degrees Kelvin higher critical temperature than the niobium mentioned before, it's past some threshold of cooling. So cooling below 10 Kelvin is much harder than cooling to 10 Kelvin. So this is the first generation of prototypes, just moving that one step above. And then for determining the thickness, there are some, from the equation shown earlier, you can get some design parameters for what range of parameters will be more favorable to get the shapes of the steps that you want.
So what are the current methods to cool, and like what are like the future more efficient methods to
Okay.
cool?
So these are all cooling methods that are currently in use. So for these which go below 10 Kelvin, they use liquid helium. But even in the temperature, so okay, here, this temperature range, this can be cooled with just liquid nitrogen. So if you saw the magnetic levitation, did you do that demo? No, oops, okay. Demo later, they're using the materials like this, and that is much easier to cool. Liquid nitrogen is way cheaper than liquid helium. But since this is a fabrication challenge, we're still considering these ones, which do still need liquid helium, which has a temperature of 4 Kelvin. But in the previous case, you need to have various like pumping mechanisms. You need to replace your helium regularly. And it's an active kind of research lab where you always need a technical person working it. But with these 10 Kelvin range, you can have a closed loop system. So you wouldn't need to have some cryo engineer working with it. You can just leave it on. So if you have people that know anything in optics lab, if you have those superconducting nanowire photon detectors, they are cooled down, but you don't really need to worry about that system, and it's not too big. It just sits in your lab. That's kind of what we're picturing for this device.